This lecture, we're going to change pace a little bit, and instead of focusing on the structure of molecules, we're going to start to transition into thinking about energy as it relates to chemistry. What that requires is kind of a first lecture or quick discussion on kind of the basics and fundamentals of energy. Certainly, if you've taken some physics, you will have seen something much more rigorous and sophisticated in those courses. This is sort of kind of a baseline to get us all onto a page that we can work with as we start to look at the energetics of chemical processes. So let's get our notes in front of us. And what we're looking at are kind of the fundamentals of energy. To keep things simple, we're going to focus on the two broad types of energy. And we could break each of these down and be much more sophisticated and rigorous under certain situations and that sort of thing. But we're going to, we could, but that we'll save that for the physicists. And instead, we'll just kind of focus on what we need to know to go forward with chemical processes. So the first one I want to mention is kinetic energy. So kinetic energy is energy of a system due to motion. Energy of a system due to motion. Okay, so what we're saying here is that things that move have kinetic energy. And I want to quantify that a little bit and say things that move have positive kinetic energy. So we could actually quantify this, assign a number to it, and say there's 15, whatever units we want to use of kinetic energy. And so 15 positive, that implies that something is moving. And if instead we had a value of 30, we would say it's moving twice as much. It has twice as much kinetic energy. Okay. In contrast, things at rest have, and by rest I should clarify, that is not moving, have zero kinetic energy or no kinetic energy. And so it actually is really hard for something to have absolutely zero kinetic energy, but really, really hard. But just kind of as we're understanding what kinetic energy is, we can just say it's nice to define the 0 point. So we have the 0 point, we have the positive, and for our class, we're not going to worry about negative kinetic energy. Okay, so speeding up then, if we think about these values, causes an increase in kinetic energy. I'll put quotes around that. Speeding up causes an increase in kinetic energy. Okay, so, and then vice versa for slowing down. That is, as you slow down, you're going to decrease the kinetic energy. Now, this is related to a really important concept in chemistry and really in being a scientist in general, and that is the idea of temperature. So temperature is a very common data point, excuse me, that we like to observe about a system. So when we're talking about temperature, temperature is actually the average kinetic energy of a system. The average kinetic energy of a system. And so if we look at the terms here, this is a really important definition, really important definition. The average, and this is over all molecules in the system, put a space there. So we have all of the molecules in the system. They're kind of moving around within our system somewhat, bouncing around, jostling, gyrating, rolling over each other. And they have some, as a result, they're all moving and they have some kinetic energy. And what we're saying is we are taking the average kinetic energy of all molecules in the system, and that average kinetic energy amounts to the temperature. And that's really what a thermometer is kind of measuring. And so we have kind of two broad descriptions, many, I guess, broad descriptions, but two common descriptions for temperature that we all make. So right now, well, maybe not at this very moment as you're watching this, but certainly in the past few months, as this has been recording, we've been making a lot of hot observations. And what we're noticing about the chemicals in the atmosphere around us is that these chemicals have a high average kinetic energy. Whereas near the end of this semester, it will start to feel cold. And when it's cold, we say that we have a low. That's describing a system that has a low average kinetic energy. Okay, so that's kinetic energy. We don't really spend a lot of time thinking about how a single atom moves around, or a single atom has, or molecule has kinetic energy, but we like to think about entire systems, certainly, and what their kinetic energy is. We make temperature observations all of the time, and temperature observations, whether it's 20 degrees Celsius or 150 degrees Fahrenheit, we're always making a measurement of the average kinetic energy of that entire system, of all of the molecules. A thermometer kind of works by having its own set of molecules, and when that thermometer is exposed to a system, the kinetic energy that bombards the glass surrounding the molecules in the thermometer transfers some of that kinetic energy into the molecules in the thermometer, and that causes those molecules to expand, or that collection of molecules to expand and get to higher and higher points on the thermometer. And so once we achieve what we call temperature equilibrium, then we can make the assumption that the kinetic energy of the thermometer matches the kinetic energy of the system that we've exposed the thermometer to, and that allows us to make a reading. Okay, make a meaningful reading about our system from a piece of glass with some liquid in it. Okay, anyway, let's move on to the second type of energy that we're going to look at, and that is potential energy. So potential energy can be a little bit less intuitive. So this is our second broad class of energy. And so this is energy due to the arrangement or position of a system. So the potential energy is the energy caused by the arrangement / position of a system. Another thing that you can think about is this is the stored energy. Okay, this is not kinetic energy, so it's not moving. Okay, we don't have to think about it moving, or this type of energy doesn't result from any movement or lack of movement. It's just where something is in space-time, how something is kind of arranged its components. Okay, so it's the energy. Another way of thinking about it is it's the energy a system could have, it could potentially have, if it were set to motion. Okay, we're going to look at examples of potential energy, but before we do, I want to bring up another one of these physical laws that's really important to kind of hold on to, and that is the law of the conservation of energy. Okay, what the law of conservation of energy says is that energy is not created or destroyed. I don't know about this already. Energy is not created or destroyed. If we think about it, kinetic energy is the energy of movement. We can speed things up, seemingly create the energy, or slow things down. So this might be a little bit troubling. But if we think about it not in terms of taking away or adding energy from nowhere, instead of thinking about it that way, we're going to think about taking away or adding energy from some other source. That is to say, rather, energy changes are caused by a transfer of energy. And so a really good example of this, a really good example of how to transfer energy is we could take some kinetic energy, transfer of kinetic energy into potential energy. So we could transfer the kinetic energy into the potential energy and vice versa. Okay, that is, we could take the potential energy into kinetic energy or kinetic energy into potential energy. Okay, I really like to kind of think about this transfer idea. I really like to bring up the idea of the bowling ball on a shelf. So the bowling ball on a shelf idea. So in this, we take a shelf, and that shelf is doing what a shelf does. It's like mounted to a wall or something. It's high above the floor. And so on that floor, let's put a bowling ball. So what we say here about our system is that we have 0 kinetic energy. And let's say, just for the sake of discussion, we have 0 potential energy. I know that at the molecular level, I know as well as any chemist, I'm aware that at the molecular level, the bowling ball is not truly at kinetic energy, but in terms of like what it's rolling around or falling, that sort of thing, it's at 0 kinetic energy. And then let's say the floor is the lowest point that we can get in this apartment or whatever we're at. The bowling ball is at its lowest point, excuse me. And then what we're going to do is one of us, either you or I, is going to walk in and be strong and say, I will lift the ball. And so I'm going to add plus 10 energy, and let's assume we have some units. I'm not going to get into the units now, but some common units throughout this. So I'm going to lift the ball, and I'm going to put the ball on the shelf. So there's the floor, there's the shelf again. Now the bowling ball is on the shelf. Now the bowling ball continues to sit at rest. It has 0 kinetic energy. But what I've done is I've come in and I've added some energy from my muscles by just lifting the bowling ball and putting it on the shelf. I am introducing energy into the system. Now, where does that energy go? The energy goes into the form of potential energy. Now the bowling ball is still a bowling ball. It has not changed its molecular arrangement, but its arrangement in space and time, it's now not at the lowest point, it's now at the highest point. Gravity's interacting with that bowling ball, and if that bowling ball were allowed to drop, it would start to move instantaneously. That is, you take the shelf out of the way, and it starts to move. Okay, that wouldn't happen before. If we took the shelf out of the way at this position, if we take the shelf away, the bowling ball doesn't care. It does not change its kinetic energy. However, in this position, the bowling ball now has the potential to have kinetic energy if we take the shelf out of this situation or we give the bowling ball a nudge. And let's do that. So let's nudge the ball. Or push the ball a little bit. I know we're adding a little bit of kinetic energy to the system. You could also think about removing the shelf entirely if you want to think just purely about what happens to the potential energy. The metaphor is not perfect here. Maybe I will say we just kind of quickly go in the dead of night and just pull the shelf away. Okay, so remove the shelf. Now there's this like Wile E. Coyote moment, if you've ever seen, Looney Tunes and the Roadrunner. I mean, in reality, it's not a long moment, certainly, but the bowling ball no longer is kept in place in its arrangement in space and time by the shelf, so it just plunges downward. As it falls down, it introduces kinetic energy into the system. So it falls down, and now its kinetic energy, right before it hits the floor, is increasing, and its potential energy is decreasing. So what I wanted you to take away from this is not the deep physics of the motion of a bowling ball. I just wanted you to see how energy could transfer from the kinetic and the potential state. Okay, we started with 0 kinetic and potential, but we introduced 10 energy units into the system by lifting the bowling ball and putting it on the shelf. Those energy units were not destroyed once they were introduced into the system. Rather, they were stored as potential energy. So the potential energy of the system changed when we added 10 units by lifting the ball. And now we have 10 potential energy units. If the shelf was removed or the ball was pushed off the shelf, those 10 potential energy units would start to be transferred into kinetic energy units as the ball drops to the floor. When it drops to the floor, it dissipates that kinetic energy out to other parts of the system, and we're back to where we started with 0 kinetic energy and 0 potential energy as the ball sits on the floor. Again, don't worry too much about the deep ideas of what the bowling ball is doing, what its energy is at any particular time. Just recognize the opportunity to go from kinetic energy to potential energy. Okay, potential energy, it's stored, and then as it starts to move, it loses that potential energy unless it gets energy from another part of the system. Okay, so what's the takeaway here? In the example above, the potential energy was used to do work. So the potential energy was used to do work. Work is an actual technical physics term, and it's just kind of, if I paraphrase, it's just kind of how much something can do based on its current energy state. Okay, and you can learn a lot more about things like work in thermodynamics. It's a really important engineering and physics concept. So we did work, and what was the work that we did? We allowed the ball to move / fall to the floor. So the ball is on the floor. So hopefully this movie provided some insights into ideas surrounding kinetic and potential energy. And the goal here is not to be a master of kinetic and potential energy, but it's to appreciate where energy can kind of come from, keeping in mind the law of conservation of energy, where we cannot create or destroy energy.